Welcome to Shining Grades Online School. Today, I'll be taking you through Chemistry Paper 2 color series. Please don't forget to like, comment, and subscribe to our YouTube channel. Welcome. Starting with question number 1. The table below shows the atomic numbers of some elements represented by letters J to Q. The letters do not represent the actual symbols of the elements. Study it and answer the questions that follow. We have elements and the atomic numbers. We have element J with atomic number 11, element K with atomic number 17, L 15, L 14, L 12, P 20, and Q 19. Looking at the table that we are given, we need to understand that the atomic numbers of any element or the atomic number of any element represents the number of protons for that given element or atom. This is also equivalent to the number of electrons of that given element. This means that the atomic number 11 is equivalent to the number of electrons or protons that particular element has. So, I can use the atomic number, that is the electrons, the protons that is equivalent to the electrons, to write the configurations of each and every atom that we are given. So the electron configuration of J shall be 2:8:1. This because 11 protons equals to 11 electrons. For 17, it shall be 2, 8, 7. 15, it shall be 2, 8, 5. 14, 2, 8, 4. 12, 2, 8, 2. 20 shall be 2, 8, 8, and then 2. The 19 shall be 2, 8, 8, 1. So these are elements or atoms of elements in different groups and different periods. We have elements in period 3, and we also have elements in period 4. We have elements in common groups and others in different groups. So beginning with the question part A, write the electronic configuration of M and P, the ion of P. So for the electron configuration of M, as I've just done it, it shall be 2, 8, 4. For electron configuration of the ion of P, we need to understand that for the ion of P, it forms an ion by losing the 2 outermost electrons. So when it loses the 2 outermost electrons, we are going to have a configuration which is 2, 8, 8. And this gives each have a mark to be in a position to score 1 mark. Moving to the next question, write the formula of the compound formed when L combines with N. We need to understand that L is an element or is an atom with electron configuration 285, meaning L with 15 protons, its configuration being 285, it reacts by gaining 3 electrons to attain its duplet stability. Not octet stability, not duplet stability. There is 8 electrons in its outermost electron. That is L. And then we have N, which is having 12 protons. Its configuration is 282, which reacts by losing the 2 electrons in the outermost energy level. So this means that the valence of L is 3 and the valence of N is 2. On the rules of writing formulas, we need to understand that N is a metal and L is an unmetal. So anytime we are writing a formula, we start with the metal, so N, then L. Then we interchange their valences so that the valence of N goes to L and the valence of L goes to N. So we are going to have N3, L2, and that is the formula of the compound that is formed when L combines with N. You also need to understand that you can be allowed to use the actual elements, symbols of those given elements to write the formula. For instance, we understand that L is phosphorus and N is magnesium. So I can still write the formula Mg3L2 and still score the mark. Moving to the next question, how would the reactivity of element N and P with chlorine compare? N, as we have just seen, it has an electron configuration of 282, and then we have P. P, we saw, is 2882, 2882. These are elements in the same group. They are elements in the same group, and as we know, these are examples of alkaline metals that react by losing 2 electrons in their outermost energy level. So how would the reactivity of N and P compare? As we know, the one with larger atomic radius is always more reactive for the metals. The one with larger size is always more reactive. So we are going to say P is more reactive than N. For you to score the first mark, we say P is more reactive. P is more reactive than N. So this one is going to give you 1 mark. Then we explain. Let's explain this. Why is P more reactive than N? So P has larger atomic radius than N. P has larger atomic radius than N. Therefore, it has lower nuclear charge, and hence P has less nuclear charge. Or you can as well say, therefore, it easily loses its valence electrons as compared to N. And that gives you another 1 mark. Moving to the next question, element N combines with oxygen to form an oxide. Using dots and crosses to represent the electrons, show how the 2 elements combine. You need to understand that N is again the magnesium that we talked about earlier on. Then we are using now oxygen, that we know oxygen is always an atom or element with atoms that has 16 protons or electrons. So that means the electron configuration of oxygen, not 16 but 8, sorry, 8. So we have 8. so that the configuration becomes 2, 6. So the valence of N is 2 and the valence of oxygen is also 2, but N reacts by losing or oxygen reacts by gaining 2 electrons. So when we understand that, we need to have the ions of these particular atoms. So I begin with the metal, as I said before. So for N, going to have N with 2 H, H, and use crosses to represent N, 2H, and because it loses 2 electrons to become an ion, then I'm going to enclose with the 2 brackets, then show the ions that are lost. Then this becomes then 2 positive, 2 8. And then for oxygen, oxygen is O. We are going to use dots. Oxygen is 2, 6. So we first draw the 6 dots. The 6 dots. Then they gained 2 crosses, 2 electrons from the other side. So it is 2, 8. So again, I make it an ion by putting the 2 brackets there. And I put 2 negative to show that it has gained 2 electrons, and this is oxygen ion 2, 8. So this will give you a whole 1 mark. So that is how the electrons form, that's how the atoms come together to form the oxide of N. Moving to the next question, select the most electropositive and the most electronegative element and give reasons for your answer in each case. We need to look at what we have here. We need to understand that always the most electropositive, most of the times metals are the most electropositive. This is because they always have react by losing electrons. So they have high chances of losing electrons. So they are more electropositive. So comparing the metals that I have, the one that has high chances of losing an electron is Q. Because when you look at the other metals that we have, sodium, that is J, and also compare it with P and Q, you realize that Q has a high chance of losing electrons. So it becomes the most electropositive. And on the other side, the most electronegative is always the non-metals, which can easily gain an electron. In other words, they have smaller nuclear or less nuclear charge for the non-metals. So in our case, we have K, we have L, and we have M. When I look at them, K has high affinity of gaining electrons. So it is the most electronegative. So in my case, I'm going to say most electropositive, most electropositive is Q. Q, remember Q is potassium, Q is calcium, is potassium 2,881. It is more reactive, most reactive metal. And the reason that you are going to give it has the largest atomic radius, thus loses electrons more easily. It has the largest atomic radius, hence loses electrons more easily. Most electronegative is, in our case we have said is K, which is chlorine. So is K boson, which has the smallest atomic radius, hence readily gains electrons. It has the smallest atomic radius, hence easily gains electrons. You can still say it has high affinity for electrons. This is going to give you half a mark, an explanation half a mark, stating half a mark, explanation half a mark. That shall add up to 2 marks. Next question. State one physical and one chemical property that elements J and Q have in common. Let's look at J. J is what? J is sodium, that is 11 protons. So J has 11 protons and Q has 19 protons. So we have J and Q. So Q 19. So this is 281 and 2881. These are elements in the same group, and these are alkali metals, group 1 elements. So we are looking at one physical and one chemical property that J and Q have in common. So we are going to begin with the physical properties. I'm going to begin with the physical properties. So we begin with the physical properties. So let's write physical properties. So one of the physical properties of these metals, they have metallic luster. Metallic luster. These are metals and they have metallic luster. 2. These metals, they are good conductors of electricity and also heat. So are conductors. They are good conductors. That is for the physical properties. Let's now look for the chemical properties. The chemical properties of these metals. One of the chemical properties, we are going to look at how they react. So looking at how they react with water to form hydrogen gas. Reacts with water to form hydrogen gas. And number 2, reacts with chlorine to form metal chlorides. These are metals. So reacts with chlorine to form metal chlorides. This is just going to give you 1 mark. So the distribution is just half a mark and half a mark. In which case, we are just supposed to state 1 So in each case, we give half a mark each. Moving to the next question, what name is given to the group of elements to which element M belongs? Element M, as you can see, is an element with 14 protons. It has 4 electrons in its outermost energy level. So element M has 14 protons. 2, 8, 4, and this is basically silicon. Silicon lies in elements that we call metalloids. These are semiconductors. They are in between metals and non-metals, and we also call them semiconductors. They are found in between metals and non-metals, so we call them metalloids. Moving to the next question. Element K consists of 2 isotopes with the relative abundances 75% and 25%, and mass numbers that 5 and that 7 respectively. Find the relative atomic mass of K. So how do we find the relative mass of element that has isotopes? So we need to understand that the relative atomic mass is given by the mass of the isotope multiplied by the percentage abundance, and then you divide by 100. So what we are given the percentage abundances. So the percentage abundance, the masses. So we have the first isotope with a mass of 35, the percentage abundance of 75. Because they are two, we have another with percentage with a mass of 37 and percentage abundance of 25. And now we divide this by 100. So when we work it out, we are going to have 26, 25 plus 925 divided by 100. This gives us that 550 over 100, and therefore our relative atomic mass becomes 35.5. 35.5. So this will just give the and then 1. So that is so we work out the relative atomic mass of element elements with 2 or more isotopes. Next, Roman 2. Why is the relative atomic mass of K not a whole number? Look at the relative mass, you realize that it's not a whole number, it's a fraction, or it has decimal point, not a whole number. So why is it a whole number? The reason is because K, it exists as a mixture of isotopes. So if it exists as a mixture of isotopes, automatically we are getting the average mass. So it's because K exists as a mixture of isotopes, and that will shall give you a 1 mark. Let's look at question number 2. Question number 2. The flow chart given below shows an analysis of mixture K that contains 2 salts. Study it and answer the questions that follow. This is a flowchart derived from the topic sorts, and we need, or a student shall require the general knowledge in both sorts in Form 2 and sorts in Form 4. So we start by analyzing this particular flowchart. We have mixture K. When you add water to the mixture on filter, we obtain solid M. So we move with this route. So we form solid M. When you take solid M and we subject it to step 2, we're going to obtain a metal oxide and carbon dioxide. This shows that M is probably a metal carbonate that has undergone thermal decomposition. M could be a metal carbonate that undergone thermal decomposition, and that is how we always obtain a metal oxide and carbon dioxide gas is released. Then that metal oxide is added to nitric 5 acid, and we get a solution N. This solution N, when we add excess sodium hydroxide solution, we get a white precipitate that dissolves. So if we get a white precipitate that dissolves, we need to think of which metal ions dissolve in excess sodium hydroxide, and we realize that it's what we call ZAP. ZAP, it's zinc. We have presence of zinc ions, presence of aluminium ions, and presence of lead ions. So we are going to choose between the three. Which one could be this? Now, when I add excess ammonia, white precipitate forms that dissolves, and we need to understand that anytime we have ions that dissolves, metal ions that dissolves both in excess sodium hydroxide and excess ammonia to form a white solution, or not a white but a colorless solution, is always zinc. Zinc dissolves both sodium hydroxide and excess ammonia solution. The rest, the two, aluminium and lead ions, do not dissolve. So here we can make a conclusion that in N we have zinc ions. So these zinc ions automatically takes us back to solid M, because we noted before that solid M is a metal carbonate, then solid M is going to be a zinc carbonate. That is the analysis that we have done. And if it was zinc carbonate, automatically N becomes zinc nitrate. It becomes zinc nitrate. Metal oxide becomes zinc oxide. Learners, I think you can note how simple and easy it is to simplify this given flow chart. You need to understand that when zinc ions dissolves in excess sodium hydroxide, we will always form zinc tetrahydroxyl to conjugate. So we have zinc tetrahydroxyl that is formed, that is complex ion. This comes when we add sodium hydroxide to a precipitate of zinc hydroxide. Then when I add to excess ammonia to zinc ions, I'm going to get zinc tetraamine. So we're going to have an ion, a complex ion, which is zinc, with molecules of ammonia. And that's the reason we are calling it zinc tetraamine. Zinc tetraamine. This one we enclose with 2 positive. So with that summary on that side, we can now move to the other route where after adding water, it was a mixture. So it was zinc carbonate, and then we have solution L. This solution L, when it is added excess sodium hydroxide, a portion of L, and it was warmed, colorless solution and ammonia gas was produced. So when I see a colorless solution being formed, and there's a gas that is being produced, and the gas is ammonia, when it comes to my mind, L must be an ammonium salt. It must be an ammonium salt. So the question is ammonium what? So L is an ammonium salt. Let's move to the other route so that we make a conclusion. When I add silver nitrate followed by nitric 5 acid, a white precipitate is formed, and this, we summarize this based on the solubility of chlorides. This because we know anytime we see silver nitrate, we think of the chloride or the carbonate. But now, silver nitrate being added, and then acid is added, it's also added, a white precipitate is formed. The white precipitate formed does not dissolve. So anytime I see this, it is only the chloride of silver that cannot dissolve. Because we know the chloride for lead, it always dissolves in addition of acid. So this shows that this one was our chloride ions. There are chloride ions here. So the chloride ions create ammonium salt. So this means that L was ammonium chloride. L was ammonium chloride. And that means when we add excess sodium hydroxide, we are able to get the ammonia. And that is what happens is that when I have ammonium chloride, I add sodium hydroxide, we obtain going to obtain ammonia gas, water, going to obtain ammonia gas, also going to obtain water, and at the same time we are going to obtain a salt which is sodium chloride, and that is the colorless solution that we are talking about. So here, with that analysis, I can easily answer the question. Name substances L and M. L, we have said, it is ammonium chloride. And because I've been taught to name, I'll not write a formula. So just write the name, ammonium chloride. Chloride. This will be awarded 1 full mark. M, it's here. It's a solid M, and solid M is zinc carbonate. Zinc carbonate is zinc carbonate. Again, this is going to be awarded 1 full mark. Going to the next question, what condition is necessary for step 2 to take place? Let's see step 2. Step 2, yes, step 2 is it. It is required for that process to occur. So we need it. And that is the condition that is needed in that particular step. Let's look at step. Beginning with question part C. State the color changes that the metal oxide undergoes when hot and cold. we need to look at the metal oxide. The metal oxide that was formed after the thermal decomposition was zinc oxide. Learners, we have some metals when they are decomposed, their oxides have different colors when they are hot and when they are cold. A good example is lead oxide. Lead oxide, when hot, it is always orange in color. When cold, lead oxide is always yellow in color. That is when cold. Another one is zinc oxide. Zinc oxide, when hot, it is always yellow in color. That is when hot. And when cold, zinc oxide, it's always white in color. So given looking at the question that we have at hand right now, zinc oxide, when hot, it is yellow, and when cold, it is white in color. So this gives us half a mark in each case. Moving to the next question. When sodium hydroxide is added to a solution N, white precipitate is formed, which later dissolves when added in excess. Give the name and formula of the complex ion formed. We need to understand that solution N is zinc nitrate, meaning the solution contains zinc ions, and when we add excess sodium hydroxide to zinc ions, zinc hydroxide precipitate dissolves in excess to form a complex salt. And we had seen before, when I add a few drops of sodium hydroxide, we always obtain a precipitate of zinc, and this precipitate is zinc hydroxide, which is a solid white precipitate. When I take, this is when we have added a few drops of zinc or of sodium hydroxide. When I add in excess, we find the white precipitate, which is solid. I add excess hydroxide, we obtain a complex salt, which is zinc tetrahydroxyl, which is a complex salt plus 2 molecules of hydroxyl. So this is what we call the ziget, and it is a complex salt. So the complex salt that we are being asked to give the formula and the name, we have the formula being zinc tetrahydroxyl, or we can also call it ziget. So I can start by writing the formula. So the formula, we have zinc tetrahydroxyl. The name, we have zinc tetrahydroxyl. It's the official name, zinc, or the UPAC name, zinc tetrahydroxyl. You can also call it ziget. So this is 1 mark, and the name is 1 mark. Moving to the next question. Next question. Explain why it was necessary to add water to mixture K and filter. Why do we add water? We need to understand that K is a mixture of a soluble and insoluble salt, and that's the reason we add water, so that we can be in a position to separate the two components or the two salts. So the correct answer is K is a mixture of a soluble and an insoluble salt. Insoluble salt. That one gives you 1 mark. Question part next. 7 grams of a mixture of sodium carbonate and sodium chloride were dissolved in water. The solution was found to neutralize 25 cubic centimeters of a solution of nitric acid that contains 63 grams per liter. Determine 1. The molarity of the acid. We need first to find out the molarity of the acid, and we need to understand that we are already given the concentration of the acid, but in grams per liter. So what we need is just to convert this into moles per liter, which is molarity. So in this case, I am going to have the formula of nitric 5 acid. Nitric 5 acid is HNO3. Given the relative masses of these atoms that forms nitric 5 acid, we have 1 plus 14 plus 16 times 3. So I'm going to have 15 plus 48, and this gives us 63. So we need to understand that 1 mole is equivalent to 63 grams, as we have noted here. That is the relative formula mass. We ask ourselves, what about again 63 grams that we have? 63 grams. So we are automatically going to get 1 times 63 divided by 63. We get 1 mole. Or we can just determine the molarity by taking, that is mass per liter, that is mass per liter over the relative formula mass. That is the simplest way to do it. So I'm just going to have 63 grams per liter divided by 63, and I obtain 1 mole, which is equivalent to 1 mole. So this is just 1 mark. So the next question is determine the moles of sodium carbonate present in the mixture. How do we determine the moles of sodium carbonate? We need first to determine the moles of the acid used. Because we already know the concentration of the acid, we understand that it is the sodium carbonate that reacted with the acid. The sodium chloride do not react with an acid because it is already a salt. Sodium chloride is a neutral salt. It does not react. So in this case, I'm going to determine the moles of the acid that reacted with the carbonate. So I'll begin by asking myself, I understand that 25 cubic centimeters of the acid was neutralized. Neutralized was neutralized by the base. So in this case, I'm going to have, I have my the concentration of the acid, concentration of nitric 5 acid. In our case here, we know it is 1 molar. We know 1 molar represents 1 mole in 1 liter. 1 mole in 1 liter. So we ask ourselves if 1 mole of nitric 5 acid was present in 1 liter, which is 1,000 cubic centimeters. What about the 25 cubic centimeters that were used? So what about 25 cubic centimeters? In this case, it's going to be 25 multiplied by 1 divided by 1,000. And this gives us, we have 0.025. 0.025 moles. So these are the moles of the acid that reacted with the carbonate. So I can determine the number of the moles of carbonate by using the mole ratios. So I need to write the equation. So I have sodium carbonate, which is a solid, plus nitric 5 acid, which is aqueous. They are going to give us sodium nitrate plus water plus carbon dioxide. It is aqueous, it is liquid, and then carbon dioxide is a gas. So what am I going to do? I balance the equation, and we realize that sodium is 2, sodium is 2, sodium is 1, so I put a 2 here. And sodium is 2, sodium is 2, carbon 1, carbon 1 on the other side, oxygen 3 plus 3, 6, oxygen 6, oxygen is 6, 6 plus 1, 7 plus 2, 9. So how do we balance the equation? We have sodium 2, carbon 1, oxygen 3 plus 3, 6, oxygen 6. So I put, look at hydrogen. Hydrogen is 1 here, hydrogen is 2 here, so I balance the hydrogen here. Hydrogen 2, hydrogen 2. The oxygen now becomes 6 plus 3, 9. The oxygen is now balanced on the other side, 9, 9. So in this case, the mole ratio becomes 1:2. And I understand that the moles of the acid that were used is 0.025 moles. So how do I get the moles of the carbonate used? So I just do the cross multiplication, and I will just divide by 2. So it's going to be 0.025 divided by 2, and I'm going to get 0.0125. 0.0125. So those are the moles of the carbonate that were used. So here, writing the equation, I have a mark. Determining the moles of the acid here, I have a mark. And finding out the mole ratio here, 1 mark. So those are 2 marks. The percentage of sodium carbonate in the mixture. How do we determine the percentage of sodium carbonate in the mixture? We need first to determine the mass of sodium carbonate, that is the relative formula mass of sodium carbonate, and we then determine the moles that were used. So here, I'm going to look at the relative formula mass of the sodium carbonate. relative formula mass of sodium carbonate, we have 23 times 2 plus 10 plus 16 times 3, and when I work out this, I'll get 106. 106. So that is the relative formula mass. Then I already have the moles of the sodium carbonate that were used. So with the moles, I can determine the mass of the sodium carbonate that was reacted with the acid. So in this case, the moles of sodium carbonate used is 0.0125 moles. These are the moles. So if these are the moles, then what does it mean? We are being asked to determine the percentage. So we need to understand that we were given 7 grams of a mixture. So the percentage of sodium carbonate in the mixture, the percentage of sodium carbonate in the mixture, the mass of sodium carbonate, we determine the mass of sodium carbonate used. So how do we get a mass? Mass is given by RFM multiplied by the moles. So we have 106 multiplied by 0.0125. So when I do the calculation, I'm going to get 1.325 grams. So this is the mass of sodium carbonate that was present in the mixture. So how do I do it to get the percentage? I'll take the mass of sodium carbonate that was present in the mixture, then I divide by the total mass of the mixture, then I multiply by 100. When I do the calculation, I'm going to get 18.93%, and that is the correct answer. So yeah, getting the relative mass, have a mark. Getting the mass is up, and then is to 2 marks. Moving to the next question, the diagram in the figure below shows some natural and industrial processes. Study it and answer the questions that follow. We need first to analyze the flow chart for us to be in a position to understand it. These are carbohydrates in plants. These carbohydrates are, or they lead to formation of simple sugar, and this simple sugar is passed through a certain process that leads to formation of ethanol. And we know in science this reaction, we call it an anaerobic reaction, that occurs in plant cells that leads to formation of ethanol. So a simple sugar taken through this particular process leading to formation of ethanol process, we also call it fermentation. This process leads to formation of ethanol. The formula of ethanol is CH3 CH2 OH. You can still write CH5 C2 CH5 OH. Ethanol is passed through another process that leads to formation of an alkene, which is ethene, and it is done in presence of a temperature of around 180 degrees Celsius, and a drying agent which is concentrated. So here we have condition of 180 degrees Celsius, and we also need conc sulfuric acid that leads to formation of ethene. Then ethene undergoes another process that leads to formation of a polymer. And this polymer will automatically be a polyethylene. This is an addition polymerization. It's going to be polyethylene, and you can easily write it because it was from ethene. Then we break a bond, then polymer ethene. Then ethene on this side at this point also undergoes another process that leads to formation of another product, and this product is what we call ethane 1,2-diol. And this process, we have ethene being converted to ethane 1,2-diol, and you can see it has two OH groups, so we call it ethane 1,2-diol. And then it undergoes another process by being added something else that leads to formation of a polymer that we call toluene. So the reactant that leads to formation of toluene when ethane 1,2-diol reacts with another monomer from a different compound, it forms toluene, and that compound is always known as benzene 1,4-dioic acid. This one is what we call benzene 1,4-dioic acid. It is 1,2 benzene 1,4-dioic acid. Then we have carbohydrates being taken through another enzymatic reaction, which leads to formation of vegetable oils. So with vegetable oils, we have a soap being formed, and through process B, the process that leads to formation of a soap, we call it saponification. So with that simple summary, we can try to answer the questions that follows. We identify processes A, B, C, and D. Process A, as we saw before, it is fermentation. Process B, I call it dehydration. Process B is dehydration. Process C from ethene to polymer, it is polymerization, and specifically addition polymerization. This addition polymerization. And then D it's here. We have said the process that leads to formation of soap from vegetable oils, we call it saponification. Next question. State the reagents and conditions required for the processes B and D to take place. So we have seen process B is dehydration. Dehydration, the reagent that is always required there, it is concentrated sulfuric acid. We have been taught to state. So here I can just name it concentrated, write in full, sulfuric acid. Then the condition that is required, we need a temperature of around 180 degrees Celsius. Don't give a range, just give a specific temperature, 180 degrees Celsius. Process D, the reagent there is always either concentrated potassium hydroxide or concentrated sodium hydroxide. So here we have either concentrated potassium hydroxide or concentrated sodium hydroxide. That is what's added to the oils and fats that then leads to formation of a soap. The condition that is required here is heating to boil. So we heat to boil. Heat to boil. Question part C. Describe how process D is carried out. Process D is saponification. How is it carried out? We start by mixing the vegetable oil with concentrated sodium hydroxide. So we say mix vegetable oil with concentrated potassium hydroxide and stir as it boils. And stir as it boils. Add sodium chloride. Add sodium chloride to precipitate. Add sodium chloride to precipitate out the soap. Precipitate out the soap. Then allow the mixture. Allow the mixture to cool and settle. Allow the mixture to cool and settle. Then rinse the soap. Rinse the soap with distilled water. With distilled water. That gives you 2 marks. Mixing the oil with sodium hydroxide, the have a mark. Adding sodium chloride, have a mark. Allowing the mixture to cool, have a mark. And rinsing the soap, have a mark. That gives you 2 marks. Stage 2 additives used to improve the quality of soap. Stage 2 additives used to improve the quality of soap. Once you prepare the soap, you can make the soap to be of higher quality. That is by adding either perfumes, addition of perfumes. So one of the additives is perfumes. You can also still add dyes to give it good colors. You can also add antiseptics. Antiseptics. You can also add bleaching substances. Bleaching substances. So just 2 shall give you 1 mark. Moving to the next question. State the reagents required in step F and G. Let's look at step F and G. Step F, it is the conversion of ethene to ethan 1,2-diol. So process F, we need acidified potassium manganate 7 because the process is oxidation. It is actually oxidation that is taking place here. You can still add acidified potassium dichromate 6. So here, F, the reagent that is needed there is acidified potassium manganate 7. Then G, process G, it is polymerization. This is what we call condensation polymerization that leads to formation of pterylene. And the reagent, as we saw before, it is benzene 1,4-dioic acid. The reagent there, it is benzene 1,4-dioic acid. The formula for this acid is the formula of the acid. The formula of the acid benzene, we have first to have a benzene ring. Then we have a carbon with oxygen molecule, then OH, and on the other side we still have the same. So we have carbon, oxygen, and then OH. This is the formula for benzene 1,4-dioic acid. So why are we calling it 1,4? We have carbon OH. It is carbon 1, carbon 2, carbon 3, carbon 4. So one is at carbon 1, another one is at carbon 4. So let's draw the structure of pterylene. The structure of pterylene, which is now the polymer, we need to understand how we obtain it. So if I can try to show the condensation polymerization, I'll begin with the first monomer. So the first monomer, monomer 1, which is then 1,2-diol, we have HO, CH2, CH2, OH. That is monomer 1, which is then than 1, 2 dioic acid, than 1, 2 diol, not dioic acid. And then we have monomer 2. Monomer 2, it is our benzene 1,4-dioic acid, which is HO carbon with oxygen, then a benzene ring, then H. So those are the two monomers that we are going to combine that will lead to formation of our polymer. And our polymer is going to be pterylene. So in this case, I'm going to start with the first monomer, H. Oxygen. How do you do it? In condensation polymerization, we have this hydrogen at this point here. It is going to combine with the OH on this side. Then we shall have this OH combining with the H at this point here. So we have this and this. So we remove those parts, and when you check, we are going to remain with something like this. We are going to have oxygen, then we have carbon and 2H, carbon and 2 hydrogens, then we have another carbon and 2 hydrogens, then we have the O yenye ilibaki pale kwa benzene ring, that is the benzene 1,4-dioic acid. So you're going to be left with O, then the carbon that has been attached to oxygen, then the ring itself. Then on the other side, you are going to be left with carbon with the oxygen, and we shall be left with lost hydrogen on this side and oxygen on something salt. That is our terylene. That is our terylene. That is our terylene. Our polymer going to be our terylene, our polymer. That's how it is done. Let's now move to the next question. Name the polymer formed in step C. Let's look at step C. Our step C is the polymerization, the addition polymerization of ethene, and the polymer in step C is polyethene. It is polyethene. 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 State one disadvantage of the polymer named in G Roman 1. So this particular polymer is one of the non-biodegradable polymers that you obtain. So one of the disadvantage is it is non-biodegradable, not decomposed, is not composed by living organisms, so it is biodegradable. It is non-biodegradable, hence causes pollution. Hence causes pollution. Again, it produces toxic gases when burned. It produces toxic gases when burned. So only one is enough to give you 1 mark. Let's move to the next question, number 4. Food biogas is made from organic waste. A Form 4 students set up the apparatus below to investigate the composition of biogas, study the setup, and use it to answer the questions that follow. Learners need to understand that biogas is a combination of an alkane, which is methane, and carbon dioxide. So when this biogas is passed through calcium oxide, what happens there is that methane reduces calcium oxide. So in this case, we also have uses copper 2 oxide, sorry. We have calcium oxide at this point, and this one is just a drying agent. This one is just to dry this particular biogas. And then it's passed through copper 2 oxide, and a reaction occurs there. So after the reaction occurs there, it is the reduction of copper 2 oxide that leads to formation of copper solid which is a brown substance. Then we need formation of water and carbon dioxide, and the water shall be formed in test tube Q. So automatically P is water, then X shall be copper solid. Then we have Y, which will be the gas that is going to be released, and this gas, as you have seen, will be carbon dioxide. Carbon dioxide. So what is the function of calcium oxide? It is used to dry the biogas. Used to dry the biogas. Name product P. Product P shall be water, and product Y shall be carbon dioxide. You need to understand that methane shall react with copper oxide, and you are going to obtain copper, which is a solid. You are going to obtain carbon dioxide, and you are going to obtain water. And that is what is actually going to happen in the combustion tube at this point. That is what is going to happen there. And that's the reason we are saying that P, because you can see it is ice cold water, so the water vapor is going to be condensed there. You're going to collect water at P. So P is water, while the gas is going to be obtained at the side or syringe. So we have Y being carbon dioxide. Carbon dioxide. Give the two observations made in tube X. The first observation is that you're going to see black solid change into brown, because copper 2 oxide is black, changes to brown copper solid. So black solid changes to brown. That is one observation. And you're also going to see droplets of colorless liquid forming on cooler parts of the tube. Colorless liquid forms on the cooler parts of the tube. Forms on the cooler parts of the tube. Then part D, Roman 1, name the type of reaction taking place in test tube X. The test tube X, whatever is happening there is a reduction oxidation reaction, so this is a redox reaction. This is a redox reaction. And why a redox reaction? We can see that methane is oxidized to carbon dioxide and water, as copper 2 oxide is reduced to copper solid. Write the equation for the reaction. So writing the equation for the reaction in the above, Roman B, Roman 1. So we have copper oxide, it is a solid. It is reacted with methane. Methane is a gas at room temperature. Then this leads to formation of copper solid. Carbon dioxide, which is a gas, and water is water is formed as a liquid before it is condensed. So when I look the balancing copper 1, oxygen 1, oxygen 2, 3, then carbon 1, hydrogen 4, hydrogen 2. So I try to balance the hydrogen becomes 2. I balance the oxygen becomes 4, so I balance the oxygen with 4 here. Then copper becomes 4, I put a 4 there, and the equation becomes balanced. Please don't forget to write the state symbols and balance the equation for you to score one mark. Next question. What elements are present in biogas? What elements are present in biogas? In this case, we are being taught to identify the elements, not this what substances are present or components, but the element that forms biogas. Biogas is basically methane. So the elements there, we have carbon, and we also have hydrogen. So each have a mark. Explain why one tube in boiling tube Q. Explain why one tube in boiling tube Q is longer than the other. So when you look at the boiling tube Q here, we have this tube and this tube here. One of them is longer than the other. And why the case? So this is done to prevent backflow of carbon dioxide and water vapor into the combustion tube. So this is to prevent backflow of carbon dioxide and water into the combustion tube. So the carbon dioxide gas and water vapor, they can be absorbed back to the combustion tube if the tubes were of the same size. So why was ice used in the experiment? The ice was used to condense the water vapor to liquid. This is the ice. This is the ice. Why was it used? To condense the water vapor to ice, to liquid water, to condense the water vapor to liquid. The volume of gas Y was found to be 240 cubic centimeters at room temperature and pressure. Find the mass of copper 2 oxide that reacted with methane. So here, you need to understand that carbon dioxide is the gas that was produced. So if I can write down the equation once again, I had methane reacting with copper 2 oxide, leading to the formation of copper, carbon 4, and water. We have balanced the equation 4 at the copper 2 oxide and also with 4 at copper and 2 at water. So 4 and 2. So the ratio is 1 is to 4 is to 4 is to 1 is to 2. So we are being taught to find out the mass of copper 2 oxide that reacted with methane. We already have the volume of carbon dioxide that was formed. And we need to understand that at room temperature, this is where the Kcse law comes in, that the volume of any given gas is equivalent to a given amount or number of moles, or they have the same number of moles. So in this case, at room temperature and pressure, we can determine the moles of Because at room temperature we know it is 24,000 cubic centimeters. So we determine the moles of carbon dioxide. So moles of carbon dioxide formed, we ask ourselves if 1 mole of carbon dioxide is in 24,000 cubic centimeter. Then we ask ourselves what about the 240 cubic centimeter. So if that is the case, I take 1 times 240 divided by 24,000, and here we shall obtain 0.01. So with the moles of carbon dioxide, I can use now the mole ratio to determine the moles of any other reactants or products in our equation. So the mass of carbon 4, now I can first get, because we want to get the mass of carbon 2 oxide. The mass, first I get the moles of copper 2 oxide. The moles of copper 2 oxide. In this case, the mole ratio between carbon 4 and copper 2 oxide is 1:4. And I already have the moles of carbon 4, which is 0.01. So automatically this one becomes 0.04 moles of copper 2 oxide. The relative formula mass of copper 2 oxide, we are given the relative atomic masses, so 64 plus 16, and this is equivalent to 80. So how do I get now the mass? Mass is given by RFM, or relative formula mass, multiplied by the moles. So here I'm going to have 80 multiplied by 0.04 moles. And the mass of copper 2 oxide was 3.2 grams. That is the correct answer. This is the correct answer to this particular question. Next question, number 5. Define the following terms. Define the following terms. Solubility. What is solubility? Solubility is the maximum amount of solute, is the maximum amount of solute that can saturate 100 grams of solvent, in this case water, at a given temperature. At a given temperature. That is the definition of solubility. Then we have saturated solution. Saturated solution is a solution in which no more solute can dissolve at a given temperature. That is what we call a saturated solution. This gives you a whole mark. Then we have part B of the question, number 5. The amount of gas X that can dissolve in water at different temperatures is shown in the table below. We have temperature at 5 degrees Celsius, the solubility is 150 grams per 100 grams of water. At 10 is 120 grams per 100 grams of water. At 20 is 75 grams per 100 grams of water. At 25 degrees Celsius, the solubility is 58 grams per 100 grams of water. At that 5, the solubility is 40 grams per 100 grams of water. At 50 degrees Celsius, solubility is 24 grams per 100 grams of water. And at 56, the solubility is at 21 grams per 100 grams of water. When you look at the trend of this solubility, you realize that as the temperature increases, solubility goes down, and this is common in gases. Solubility goes down as the temperature increases. So as the amount of temperature increases, the solubility of that particular gas also increases because the kinetic energy increases, making the gas to get out of the solution. So let's now try to answer the question that we have at hand. Plot a graph of solubility, which is the mass of gas X, against the temperature in the grid provided. So when you are taught to plot a graph, where do you start? You are taught to plot a graph, where do you start? So plotting a graph of solubility against, so the solubility is going to be on the y-axis. Solubility is going to be on the y-axis. So you will allow me to have my graph. So I have to choose a scale. In my case, I'm going to choose on the y-axis. I'm going to break the first box. I'll start at point 0. Then I'm going to use 10 small squares to represent 20 grams per 100 grams of water. So I shall have 20, then 50, 80, 50, 40, 160. Then I label, this is going to be solubility. Given per grams per 100 grams of water. And then I'm going to use 20 50%, 10 degrees Celsius, sharp 10, 20, 30, 40, 50, then 60. This is temperature. Degrees Celsius. So I start plotting my graph. Our graph is 5, 150. So we have 5, 150. So 5 at the middle, then 150. Five, 150. At that point, then we have 10, 120, 10, 120, 10, 120. Then we have 20, 20, 75, 20, 75, that's 60, 70, 75 is going to be two small squares above 70. So we have 20, 25. Then we have 30, not 30, 25, 58, 25, 58. 58 is going to be one small square below 60, 25, 58. Then we have 35, 40, 35, 40. Then we have 50, 24, 50, 24. 24 is going to be one small square from 20 on top of 20. So that is 24, 50, 24. And then lastly, 55, 56, 21. So we have 56, 21, 56, 21. So very accurate. So we have our curve. Now we can move to the other questions. The curve was 3 marks. Scale, 1 mark. Plotting, 1 mark. And the axis, 1 mark. And that is equivalent to 3 marks. Let's look at the questions after the graph. From the graph, determine the mass of gas X that would dissolve in 1 liter of solution at 20. So we need to understand that the mass of gas X that would dissolve in 1 liter of solution at 20. degrees Celsius. So what I'm going to do, I'll determine the solubility at 20 degrees Celsius. So at 20 degrees Celsius, I'm going to pick my ruler and determine solubility at 20 degrees Celsius. And at 20 degrees Celsius, I notice that the solubility is 74 grams per 100 grams of water. So at 20 degrees Celsius, solubility is 74 grams per 100 grams of water. So I'm being told to determine the mass of gas X that will dissolve in 1 liter. So here I'm looking at the mass. So if 74 grams were dissolved in 100 grams of water, I ask myself, what about 1,000 grams of water? So here, just do the cross multiplication. 74 times 1,000 divided by 100, and you're going to get 740 grams, and it is in 1 liter. So the mass here is 740 grams per liter. Then we have the question part B, the temperature at which a liter of solution contains 400 grams of gas X. So here I will just do the calculation. So if at 400 grams is in 1 liter of water, I'll ask myself, because we're told the temperature at which, because our graph is at, we're using 100 grams, so I'll ask myself, what about 100 grams? And when I do the working, I'm going to take 400 multiplied by 100 divided by 1,000, and here I shall get 40 grams per 100 grams of water. Once I've determined the solubility, I read from the graph the temperature. So from the graph at 40, that is at a solubility of 40, I use my ruler and determine the solubility at 40. Determine the solubility at 40. When I determine the solubility at 40, I notice that the solubility, the temperature is 35, and everybody can see it is at 35. So the solubility, the temperature there is 35 degrees Celsius. So this can differ depending on the scale that you have used and the graph that you have drawn. So you read and you show using a dotted line on the graph. So here we have tackled our graph. Let's now move to part C of the question. Part C of the question, we are told that the table below shows solubilities of two salts A and B at various temperatures. We have salt solubility and at 20 and solubility at 50 degrees Celsius. So meaning it's cooling from 50 to 20. We are told that a mixture containing 10 grams in 100 grams of water of A. So only 10 grams of A. So 10 grams of A and 100 grams and 22 grams in 100 grams of water of B. So this is 22 grams. 22 grams. So we are told name the salt that will crystallize out and determine the mass of the crystals. When I look at A, focus on salt A. At 50, solubility is 70 and I only have 10, meaning if the solubility is 70 and I have 10, my 10 is already in solution, so no crystals. No crystals. Then the same salt A at 20 degrees Celsius, solubility is 30 and I only have 10, so no crystals. Salt B, solubility at 50 is 25 and I only have 22, meaning my 22 is already in solution, no crystals. Then at 20, solubility is 14 and I have 22, meaning I have 8 grams of this salt crystallizing out, because solubility is 14 and I have 22 grams of the salt. So the salt that crystallizes out in this case is salt B. Salt B. Mass of crystals, we have 22 minus 14, which is 8 grams. 8 grams. So naming the salt 1 mass, determining the mass 1. Question number 6. The following diagrams shows allotropes of sulfur. Study them and answer the questions that follow. Identify allotropes X and Y. We have two main allotropes of sulfur. We have aerobic sulfur and monoclinic sulfur. Aerobic sulfur looks like as you can see, X. So X is the aerobic sulfur. This is the allotrope of sulfur, and the one that is stable at or below 96 degrees Celsius. Then the other one is automatically monoclinic sulfur. It is always stable above 60 degrees Celsius. So identify the allotrope stable below 96. It is X. You can call it X, or you can also call it aerobic sulfur. Aerobic sulfur. And the one above that is stable above 96 degrees Celsius is 1. And you can also call it monoclinic sulfur. Which name is given to the temperature of 96? This 96. So that we have aerobic, we have this 96 degrees Celsius. Aerobic being stable below 96. And monoclinic being stable above 96. What is this 96? This 96 degrees Celsius, this temperature we call it transition temperature. It is the temperature that we use to determine which allotrope. Is it monoclinic or aerobic? We call it the transitions, that transition temperature found in between the stable temperatures of monoclinic and aerobic. So we call it transition temperature. Monoclinic transition temperature. Let's now move to part B of this question. Study the flow chart below and answer the questions that follow. We have yellow solid A. Yellow solid A is reacted with concentrated sulfuric 6 acid and we obtain gas B and water. And then most litmus paper is used in this case. So we are being told yellow solid A is what? Yellow solid A is reactive to sulfuric 6, as this is one of the chemical properties of sulfur. Sulfur is we know concentrated sulfuric 6 is a strong oxidizing agent, so sulfur can reduce this oxidizing agent. So yellow solid A is always sulfur. It reduces concentrated sulfuric 6 acid to sulfur, 4-oxide, and water. To sulfur, 4-oxide, and water. When this gas is tested without moist blue litmus paper, it turns to red and it is later bleached. We're going to see that in the question. So we have named solid A. Our solid A is sulfur. Our gas B is sulfur 4-oxide. Please don't write a formula, name the substance or name the compound. Name the substance. Write an equation for the reaction between solid A and concentrated sulfuric 6 acid. Our solid A is sulfur. Sulfur is a yellow solid. I react it with concentrated sulfuric 6 acid. It is a liquid, and I obtain sulfur 4-oxide gas. Then I obtain water. I balance sulfuric 6 acid with 2, sulfur 4 with 3, and water with 2. That equation will give you a whole 1 mark. State Roman 3. State and explain the observation made on moist blue litmus paper. As we have seen, the moist blue litmus paper is first turned to red and then it is bleached. This is because of the presence of the sulfite ions from the phosphoric acid that is formed, that leads to the bleaching of the blue litmus paper. So the answer in our case is a moist blue litmus paper. A moist blue litmus paper turns to red and then gets bleached, or we can say turns to white. So we explain by saying that sulfur oxide gas dissolves to form acidic solution which contains sulfite ions. Which has a bleaching property. And of course, the hydrogen ions in the acid turns the blue litmus paper to red. So that is the explanation under that particular question. Let's look at the next question. The setup below was used by a student to prepare and collect hydrogen sulfide gas. Sorry. Study it and answer the questions that follow. So this question comes from the topic sulfur and its compounds. In the preparation of hydrogen sulfide gas, hydrogen sulfide gas, learners as seen in that particular part, it's prepared by reacting dilute hydrochloric acid and an appropriate metal sulfide. The most appropriate metal sulfide that you learned is iron 2 sulfide. So this means that solid H is iron 2 sulfide. So the first question, we are being told that complete the setup above to show how hydrogen sulfide is collected. And in this case, we are going to ensure the gas is collected when dry. So I complete the setup by first I pack the U-tube with an appropriate drying agent. In my case, I'm using anhydrous calcium chloride, and then I collect the gas by downward delivery method. So I use downward delivery method to collect the gas. So in my case, this is anhydrous calcium chloride, and then this is dry hydrogen sulfide gas. This ensure the lines are complete for you to score the answer, the mark on workability. Ensure your lines are complete. So that is how I complete. So of course, one of the mark is going to come. We have 2 marks. One of the mark is going to come from our mark collecting or collecting the gas, the method of collection of the gas. Another our mark is going to come from drying agent, and another whole mark is going to come from the workability. So we have a drying agent. We are going to have a mark, method of gas collection. We are going to have a mark, and then workability. We have one whole mark totaling to 2 marks. Moving to the next question. Give the identity of solid H and write its formula. So the identity of solid H, as we have seen, it is iron 2 sulfide. Iron 2 sulfide. Its formula is FeS. Iron 2 sulfide. I have a mark. I have a mark. Define the term enthalpy of displacement. Question number 7. So what is the meaning of enthalpy of displacement? As seen in form 4, energy changes. So enthalpy of displacement is the energy change that occurs when one mole of a substance is displaced from a solution of its ions, from a solution of its ions. That's what we call the enthalpy of displacement. Roman 2 of the question. In an experiment to determine the molar heat of reaction when magnesium displaces 1.5 grams of magnesium powder is displaced, 1.5 grams of magnesium powder were added to 25 cubic centimeters of 2 molar copper 2 chloride solution. The temperature of copper 2 chloride solution was 25 degrees Celsius, while that of the mixture was 43 degrees Celsius. Given the specific heat capacity as 42 joules per gram per Kelvin, and the density of the solution as 1 gram per cubic centimeter, and the relative mass of magnesium as 24, determine the molar heat of displacement by magnesium. So we are aiming at determining the molar heat of displacement of copper by magnesium. So we need to begin by understanding how we determine the enthalpy change. In this case, the enthalpy change is given by the formula mass C delta T, where M is the mass of solution, C is the specific heat capacity, which is given as 4.2 joules per gram per Kelvin. Then we have the change in T. The change in temperature is 43 minus 25, and this is equivalent to 18 Kelvin. So how do I determine the enthalpy change? Enthalpy change should be given by the mass of solution. We are going to get the mass 25 multiplied by the density, we shall get 25 grams, multiplied by 4.2 joules per gram per Kelvin, multiplied by the change in temperature, which is 18 Kelvin. So here I'll cancel out the mass with the mass, and then I'll cancel out the Kelvin with the Kelvin, and I'll obtain energy change in joules. So it is going to be 1890 joules, and it is given, it is in joules because the mass was in grams. So in this case I divide by 1000, and I'll obtain 1.890 kilojoules. But I'm supposed to determine the molar heat, the molar enthalpy change. I'm supposed to determine the molar enthalpy change. So how do I determine the molar enthalpy change? I must now get the moles of the substance that was or that produced that amount of heat energy. So what am I going to do? If I determine the moles of magnesium, I will notice that moles of magnesium, I will take the mass of magnesium, which was 1.5, I divide by the relative mass of magnesium, which is 24, and I'll be able to get 0.625 moles. When I try to look at this and I determine the moles of the solution, I will notice that the moles of solution, that is copper 2 chloride, will be if 2 moles were in 1,000 cubic centimeters. I ask myself, what about 25 cubic centimeter? And I'll be able to get 25 times 2 divided by 1,000. I'll be able to get only 0.05 moles. So this means that although magnesium displaced copper ions, magnesium was in excess. So I'll go with the moles of the solution to be in a position to equate with the energy that was released. And then I ask myself, what about in 1 mole? So I'll ignore the moles of magnesium and I go with the moles of the solution. So in this case, I'm going to ask myself if these moles, 0.05 moles, were in 1 point or discharged 1.890 kilojoules of energy, what about 1 mole? So here I should be determining now the molar heat energy. So in this case, I will take 1 times 1.890 divided by 0.05, and in my case, I'm obtaining 37.8 kilojoules, and in this case per mole. And because it was an exothermic reaction, then the correct answer should be negative 37.8 kilojoules per mole. That becomes the correct answer. Let's now move to the next question. The graph below shows the energy changes that occur when ice at 10 degrees Celsius is heated until it boils. When you look at the graph, it was heated at 10 degrees Celsius, negative 10 degrees Celsius. We have the temperature and then we have time taken. From the graph, determine the temperature at which ice changes into liquid. So automatically that is the melting point. The melting point, it's where it flattens. It's where it flattens, and the temperature at that point is 0 degrees Celsius. Then determine from the graph the temperature at which liquid changes into steam. Again, we determine the temperature, that is the boiling point. That was the melting point. Now we are looking at the second part where it flattens out, and that is the boiling point. The boiling point is 100 degrees Celsius. 100 degrees Celsius. The next question, determine the molar latent heat of fusion. So when a substance melts or a substance is converted from a solid state to a liquid state at its melting point, that energy that is released there we call latent heat of fusion. So because it's now molar, we are going to talk of 1 mole of a substance. So in this case, molar latent heat of fusion is the amount of heat of heat required to convert. It's the amount of heat required to convert 1 mole of a substance into a liquid, and is done at its melting point. That is what we call the latent heat of fusion. Moving to the next question, part C. Hydrogen bromide is formed from hydrogen gas and bromine gas in the following reaction. Calculate the enthalpy of formation of hydrogen bromide using the bond energies below. The bond energies are as shown below. We have hydrogen bond 436 kilojoules per mole, bromine bond 192 kilojoules per mole, and hydrogen bromide bond 368 kilojoules per mole. So I begin by rewriting my equation. So I have hydrogen gas plus bromine gas giving us 2 moles of hydrogen bromide gas. When I try to open up the bonds, I will have hydrogen plus bromine. I obtain 2 hydrogen bromide bonds. From what we are given, hydrogen bromide, it is positive 436 plus bromine, it is positive 192, and I'm obtaining 2 into positive 368. When I do my summation, I obtain positive 628 on the side of bond breaking, and on the side of bond formation I obtain positive 736. Learners, we need to understand that enthalpy change is given by bond breaking plus bond formation. Bond breaking is always an endothermic reaction, and bond formation is always an exothermic reaction. So we have to include the negative sign on the side of bond formation. So in this case, I will have positive 628 plus negative 736, because this is an exothermic reaction. So when I do the summation, I'm going to have negative 108 kilojoules per mole, and that is the correct answer to the question. That is the correct answer to the question. That gives you 3 marks. Determining the enthalpies on both sides, you get 1 mark, and getting the correct answer, you get 1 mark. So this marks the end of our presentation. Please, if you found our presentation useful, like our video, comment, and as well subscribe to our YouTube channel, Shiny Grades Online School. We shall be dropping as many videos as possible on chemistry and also on biology. So please subscribe for you to be notified whenever we post a video on the same. May God bless you as you continue watching our videos. Have a blessed moment.